Hello and welcome to my presentation. Today we'll talk about building the next generation of drivers, especially the Go and the Rust drivers, and how we optimize performance in those drivers. A few words about me. I'm Piotr Grabowski. I'm a software team leader. My team is responsible for all ScyllaDB drivers, as well as the Kafka connectors, such as the sync connector and the CDC source connector, and I have been at Scylla for the past 2.5 years. So today we'll take a short tour through different drivers, focusing on small stories of how we optimize different components of those drivers, what we learned during optimizing those drivers, and some interesting things we learned during doing this. First, we start at a short description of what a driver is, its responsibilities, and then we'll move to ScyllaDB Go driver, our new Go driver that was developed by a group of students, supervised by ScyllaDB. Next, we'll move to ScyllaDB Rust driver, our own Rust driver written from scratch that was meant to be used with Scylla first. And this is our own project started from the beginning. And next we'll talk about some interesting new initiative to implement different bindings to ScyllaDB Rust driver to use its performant core in other languages. So let's start at the introduction of what a driver is, its role. So drivers, as presented in this presentation, are the libraries and frameworks that allow you to send queries to ScyllaDB from your language of choice. The primary protocol that the drivers use is the CQL protocol. It's TCP based. ScyllaDB supports the 4th version of this protocol. This protocol is based around frames. It supports multiple streams, so multiple concurrent queries occurring at the same time over a single connection. Additionally, the queries can be sent in a compressed fashion, as well as the results in compressed fashion, reducing the time to send over the network and reducing the bandwidth needed for the network. ScyllaDB drivers support shard awareness. As you well know, ScyllaDB node is divided into multiple shards. A single shard corresponds to a physical core in the CPU, and the driver is smart enough to connect to a specific shard and to establish connections to each shard of a ScyllaDB node. So when we are thinking of the drivers, what's the components of the drivers, all the things that the drivers are responsible for. So the first role is handling the protocol format, so serialization of the serialization of different CQL frames, as well as ScyllaDB types. Next, the driver is responsible for maintaining the metadata about different tables, different nodes. A big responsibility of the driver is to route the request to a correct node, and in case of ScyllaDB drivers, to route the request to a correct shard. Additionally, the drivers handle all the low-level networking stuff. And moving from the low level to high level, the driver allows you to use convenient high-level constructs to execute and construct queries. So for example, we offer GoSQLX package that provides many useful constructs for Go language and to use with GoSQL. And Java driver offers mapper interface that makes it easy to execute and construct different queries in an object-oriented fashion. So how the driver could improve the performance? So first of all, there's shard awareness. so sending requests directly to a correct shard. There's partitioners, so this is the algorithm that determines which node to send the query to. And Scylla change data capture implements a custom partitioner, so the drivers had to be modified to take that into account. Another important optimization is LWT optimization. So Scylla offers very powerful lightweight transaction operations that allow you to atomically perform different operations, and sending a query to a single replica, consistently sending it to a single replica, helps to avoid Paxos conflicts. And the main focus of this presentation is focusing on all of the components that I shown in the previous slide, so optimizing all those hot paths in the drivers, such as serialization and deserialization, the code that routes the queries. So this code is very important as it's run at each query, and maybe some lower level optimizations like avoiding unnecessary copies, allocations, and locks. So let's move on to ScyllaDB Go driver. So ScyllaDB Go driver is our new ScyllaDB driver for the Go language. The project had an interesting start. It was developed by a team of University of Warsaw students for their bachelor's thesis. And this project was a great fit for such a program, as the implementation of Go driver was a bit of an experimental project. And the main focus of the project was performance. This was practically the sole focus of the project. When compared with an existing Go driver, GoSQL, we saw that there were many mutexes used, so avoiding mutexes was a big focus of the project. Avoiding unnecessary allocations. This is due to a Go garbage collector, which could reduce performance if lots of garbage is generated at the runtime. And interesting thing we did was implementing a faster B-tree implementation using a new function of Go, generics. So starting with mutexes, this is a comparison of how many mutexes and locks are used throughout the code of GoSQL and ScyllaDB Go driver. As you can see, in ScyllaDB Go driver, only a single mutex is used in the entire project. Only a couple calls to lock are performed. Compared to GoSQL, there are 37 mutexes. And looking at the project history, it turned out those mutexes were added gradually as the project is more mature. During all those years of developing the GoSQL driver, those mutexes added up to this large number. And unfortunately, many of those mutexes were called at the hot path of the execution of the driver. So when thinking of how to avoid this problem in our new driver, we are inspired by the ScyllaDB shared nothing architecture. So this architecture means that each component, in the case of Scylla, each shard, has its local data and avoids as much as possible sharing the data between those components. So when we started ScyllaDB Go driver from scratch, first of all, we had better overall picture of the architecture based on the existing GoSQL driver. So thanks to this, we are able to design a more clear and efficient communication between those components. And the driver code heavily uses idiomatic Go channels and atomics, which make it possible to not use mutexes. The result is that the driver only uses a single mutex, which is local to a TCP connection, and a nice effect of that is that by not using mutexes, we reduce the possibility of race conditions. The initial benchmarks of GoSQL have shown that the main issue of bad performance was the Go garbage collector. So while developing ScyllaDB Go driver, we are very careful to not do any allocations that were not needed. And the end result of that is that the driver performs 5 times less allocations compared to GoSQL. We had to meticulously design each component to avoid allocations. So it's not only some decision that had to be made in one piece of code. We used our own faster B-trees with generics, which reduced the allocation number. And additional optimization was reducing buffers owned by writers and readers. Our own B-tree implementation used generics instead of using interfaces. Interfaces unfortunately had a problem of variables escaping to the heap, and our implementation yielded 40% performance improvement compared to Google's B-tree implementation. And actually, after the project, we saw that Google's B-tree maintainers implemented a new version of B-tree that uses generics. Another interesting fact that we saw during the development was that different drivers had different characteristics of number of syscalls that they perform. And especially, we were intrigued by the number of syscalls to send packets through the network. So some of the drivers executed fewer send messages or similar syscalls, but they sent larger buffers. And from that, we saw that instead of sending each frame of CQL separately through a separate system call, it's better to wait a bit and gather maybe a larger pool of buffers and send them in a single syscall. And this drastically reduced the runtime of using our driver. So this is an example that our driver batches much more queries into a single send to syscall compared to GoSQL. This is, I think, a difference of about 5 times more. When we also did some benchmarks of our driver. So this is an example of sending many insert queries, and ScyllaGo driver was about 3 times faster compared to GoSQL. So now let's move to the ScyllaDB Rust driver. So the idea for the driver was born during a hackathon in 2020, and over the last 3 years we developed the driver much more compared to the initial implementation during the hackathon. The driver uses a Tokio framework, which is a well-known asynchronous programming framework for Rust. And we consider the driver now feature complete, which supports many features like shared awareness, the asynchronous interface with support for large concurrency, compression, SQL types, and much more. One interesting issue that we saw during the development was actually raised by a member of community. So the author of Latte, it is a benchmark tool for ScyllaDB and Cassandra. And the author tried to use our ScyllaDB Rust driver, but he saw that the driver had some problems with high concurrency of requests. And we looked in depth into the problem, and we identified that the root cause of the problem was the implementation in the Tokio framework of the futures unordered. It's an utility that gathers many features and waits for them all to finish. We saw that Tokio, in some cases due to cooperative scheduling, had to iterate over all features in this features and order structure many times. So, for example, if there were 100 features in this features unordered, we would go through this list many times. And a fix was merged to Tokio that limited the number of features that were iterated in a single poll operation, so we don't have to look through the array every time it is polled. Some ongoing efforts in ScyllaDB Rust driver. So the first thing we are working on actively is rack-aware load balancing. So the problem when running the driver in a cloud environment is that you want your nodes to be in different availability zones. However, the traffic between the zones could have additional latency and additional costs. We are implementing changes to the driver for the driver to pick the nearest rack, so the nearest availability zone, and that way the latency is improved and the cost is much less, as the traffic between the nodes in a single availability zone is free. The other optimization we are working on is implementing iterator-based deserialization. So currently the driver, when it receives a result of, for example, some select query, it tries to deserialize all the data that were received from the select into a single vec of rows. So this is problematic because we have to allocate some memory per each row in this data. So if the resulting data is 10,000 rows long, we have to perform 10,000 allocations. The solution that we are working on skips materializing all these rows into a single vector, instead offering an iterator that allows you to deserialize the data that was received from Scylla on the fly. And the third ongoing effort, which is quite a big effort, is refactoring our load balancing code. So the load balancing code is responsible for determining which node to send the query to based on the partition key. And we saw that by re-implementing this functionality, we can reduce the number of allocations and atomic operations while building the query plan. And especially this problem was seen on the happy path, so the path that is very often taken while executing the query. And now moving on to the bindings to the ScyllaDB Rust driver. This is an interesting new effort that we are working on. So while we were benchmarking the ScyllaDB Rust driver, we saw that its performance was really great. So we had an idea, why not develop a way to use this great driver through other languages? Especially we saw that the Rust driver was faster compared to the C++ driver, and both of those languages are compiled, so it should be fairly easy to talk from C++ to Rust. We also saw benefits of such approach: higher performance, easier maintenance of the solution, and fewer bugs, because we only have to fix something in a single core driver. So we started development for the C++ language. The C++ bindings that we have developed use the same API as the original C++ driver, so it's a drop-in replacement, and the bindings call to the Rust driver. The resulting project is very small compared to the original C++ driver, as it's only a layer between C++ and Rust driver. And we saw that the solution has better stability, fewer problems compared to the original C++ driver. So thank you for the presentation, and I hope you'll see and try out our driver projects.